Section 13.3, Part 2, whereas in Thomas' textbook is 13.4. We'd like to go over three special unit vectors, which they are associated with any motion problem. And those are unit tangent vector, which is defined as r prime divided by its magnitude. Normal vector, which is defined by t prime, that's like the derivative of the tangent vector divided by its norm or magnitude. And finally, binormal vector, which is denoted by b, binormal vector, which is the cross product of what? T with n. Notice the order matters, correct? So what it amounts to is in any motion problem, when you have a moving object on a curve, that object is what? That moving object is subject to three vectors, namely unit tangent, unit normal, and binormal. So when you have these three vectors, they form a plane called TNB plane or BNT plane. So that happens everywhere on the curve. So the moving object is subject to these three unit vectors. The question is, when you have this curve, this portion of the curve, and you're trying to what? We know the tangent is what? Is in the direction of the motion. Well, how do you draw the normal vector? Do you draw it like this way, or do you draw it the opposite way? It turns out the normal vector, which is also known as principal normal vector, is always drawn from the point towards the center of the what? This curve. So in other words, you always draw to the what? To the side where the curve is concaving down, not up. So in this case, as you can tell, the curve is concaving down. So there it is. Here, the curve in this portion is concaving up. So you draw the normal that way. So this would be the normal vector. So it always drawn what? From the concave down part of the curve, not up. So the question is, what does tangential, or I should say unit tangent vector is good for? It indicates the direction of the motion. What about the normal vector? It indicates how the curve turns. That's what this guy indicates. What about the binormal? Well, binormal is which is perpendicular to both what? Tangential and normal vector, is associated with a concept called torsion. Torsion is the amount of twist in the curve, on the curve, twist. Okay, not bend, but twist. In other words, the derivative of the binormal vector with respect to arc length is minus tau of s, which is what? Torsion, times the normal vector. Keep in mind, we had tau of t, which was a function of time, that was torque, but tau in terms of what? Arc length is torsion. So for a plane curve, what? The torsion is 0. So that's what this guy is good for. So with that in mind, what do you say we do a quick problem and see how would you go about finding these guys out? So once again, you have the usual what? Helix, okay? And we want to find at some point, like let's say t is equal to pi over 2, we would like to find the following. The unit tangent vector to the curve at t equals pi over 2, normal vector, so that's capital N, and binormal vector, and graph those unit vectors at point P on the curve. Okay, so remember the definition is r prime of t divided by its magnitude. So that's a unit, all of these guys are unit vectors. So in this case, you get negative sine of t, cosine of t1 divided by its magnitude, which is what? Square root of cosine square plus sine square, which is 1. And then you have what? 1 squared, which is 1. So at the end of the day, you get minus sine of t, cosine of t, 1, divided by square root of 2. Remember, we're talking about magnitude of this guy. Sine square plus cosine square plus 1. Sine square plus cosine square is 1. So 1 plus 1 is 2. You have to take the square root. So there goes the unit tangent vector. However, so this would be like at t, correct? So this would be like at t, but now at pi over 2, you would evaluate this guy, which is negative sine of t, cosine of t, and 1 over square root of 2, evaluated at pi over 2. And that would give you, what, 1 over square root of 2, negative 1, 0, 1. So hold on to this, so we can find the remaining unit vectors and graph them. Normal vector, the unit normal vector for the curve is defined as what? Derivative of the unit tangent divided by its what? Magnitude. So if you remember, t of t was equal to minus sine of t cosine of t 1 over square root of 2. So t prime of t is 1 over square root of 2. Notice square root of 2 goes for the right. And this would be like minus cosine of t minus sine of t, 0. Derivative of 1 is 0. However, if you evaluate this at pi over 2, you will end up with what? Oh, let's say 0, what? Negative 1, 0 over square root of 2. There you have it, right? So now, so that would be like, say, okay, so that's like t prime. So the magnitude of what? T prime at pi over 2 comes up to 1 over square root of 2. Therefore, we have what? T prime, or I should say normal vector, at pi over 2 comes up to, let's see now, 0, negative 1, 0. So the square roots cancel each other out. So the normal vector at pi over 2 comes up to 0, negative 1, 0. There you have it. And finally, binormal, which is what? Unit tangent at pi over 2 cross what? Normal vector at unit normal at pi over 2, which is the same as I, J, what? K, is that right? What? Negative 1, 0, 1, 0, negative 1, 0. Notice I did not take the what? Square root of 2, because that doesn't really matter. That's just on a scalar, so I'm only dealing with the vector itself. So when you do this, you get 0, 1, 1, correct? So now the idea is, how would you graph this? Well, suppose this is where what? T is equal to pi over 2 at what? On the curve at this point. So to draw these vectors on the curve, so pretend you have a different coordinate system here. This is y-axis, z-axis, and x-axis. You see it. So draw a separate coordinate system at the point you're trying to graph these guys. Turns out t is what? T is, where'd it go? Is right here, which is what? Right there. 1 over square root of 2, negative 1, 0, 1. So you go negative 1, 0, 1, right about here. So it turns out here is how the unit tangent looks like when you have a what? Kind of draw a brand new set of coordinates here. Do you see it? Okay, so that's your unit tangent. Unit normal is this guy. Okay. And binormal at what? Pi over 2 is 0, 1, 1 from here, right? You go 1 to the right, is that right? 1 front and no side movement and 1 up. So you get something like this guy. So there you have it. So now you have the TNB frame at what? T equals pi over 2. So remember, T is in the direction of the motion. N is what? Tells you how the curve turns. And binormal is what? Perpendicular to both of these guys at that specific point. So with that in mind, let's talk about these planes. So when you draw the TNB vectors, you are creating these 3 planes. The plane which is determined by the vectors B and A is called normal plane. The plane which is determined by the unit vector and binormal is called rectifying plane. And the plane which is determined by the unit tangent and the unit normal vector is called osculating plane. What's so good about this? What's so good about this? Most of the motion on the curve C happens in osculating plane. So remember, most of the motion, the curve that you have, the path of the motion occurs in this particular plane. So this is where the action happens when you're dealing with motion problems. So this is like TB frame, that's BN frame, that's TN frame. Incidentally, the vector perpendicular to normal plane is T. Vector perpendicular to this plane, rectifying plane, is N. The vector perpendicular to osculating plane is vector B. This kind of concept is used in higher level mathematics and in physics classes where you're dealing with motion problems. Thank you.